All right, welcome back. So now we are on R8. This is radical expressions. So this is our last topic from the R chapter, the review chapter. Okay, so first of all, we're going to talk about simplifying radical expressions. So let's say we had the cube root of m times the cube root of m squared to start off with. Okay, so how would we go about factoring? Well, if you recall, the cube root, any root really, is still just a power, right? So all we really are doing here is we're raising both of these to the 1/3 power. And since they have the same power, right, this is kind of going the opposite direction. If you had two terms raised, say, to the second power, you could have expanded this as a squared times b squared. You can go the other way as well, right? If they're both the same power and they're separated by this multiplication, you can put them together and put them in the same parentheses, the same set of parentheses, and then raise them to that power. And that's what we're going to do here. And essentially we're doing that exact thing. So because these have a root which has the same power, these are both the cube root, we can just throw them both under a single radical or single cube root expression. We can combine those terms together, right? So underneath this, inside the cube root, we're multiplying m times m squared. This is m to the first power. And if you have the same base and two different exponents multiplied, we just add those exponents together. So we're going to get m to the 1 plus 2, which is m to the third power. If you take the cube root of m to the third power, you just get back m. Raising something to the third power and taking its cube root cancel each other out. These are opposite operations. In other words, this would be m to the third raised to the 1/3 power. If you went ahead and used your power rule for exponents, you would multiply these would cancel out, give you m to the first power. Okay. In our second example, example B, we've got two different roots applied to this 2 in here. So first of all, you've got a cube root inside, and then on top of that, you've got the 7th root applied to this number, okay? So I think it's a little helpful to think about this first in terms of those exponents. So if we rewrite this, that cube root we can rewrite as raising this to the 1/3 power. That 7th root, we can rewrite this as raising it to the 1/7 power. And now let's go ahead and think about our power rule for exponents. A power raised to another power, we go ahead and we multiply those. So this would be the same thing as just raising 2 to the 1/21st power. In other words, that is the 21st root of 2. And that would be some horrible number. We're not going to expand this any further or try to calculate that. We're just going to leave it in this form. Simple and clean form. All right. Example C. We've got the square root of 5 times the cube root of 2. Now, the problem here is we have different bases, right? So if we were to think about these as something raised to a power, we'd have 5 to the 1/2 power, and we'd have 2 raised to the 1/3 power. Now, until now, we've thought about, well, if we've got the same base but different exponents, we can apply our rules. If we've got the same exponent, as we did in this case, even if we had different bases, we could put them under the same root or radical symbol. The problem is we have neither of them here. We don't have the same base. We have a 5 and a 2, and we have a square root and a cube root. So in fact, there's nothing we can do to simplify this. We have to just leave this as it is. Okay? We cannot combine these because both the bases and the indexes of the roots are different. In a different case, say we had both cube roots, we could throw them under the same cube root. We could make that 5 and 2 into a 10. Or if we had, say, both 2's, but we had a square root and we had a cube root, at least we could go ahead and convert these to powers and then use some product rule here for exponents. Right? But we can't do either of those things in this situation. All right? So there's not always something you can do. You have to look out for what you can actually simplify based on the bases and the indexes of the roots that you're dealing with. All right, example D. We've got the cube root of 81 x to the 5th power, y to the 7th power, z to the 6th power. So the first step here, let's expand this. Let's think about, right, we want to evaluate a cube root. So we need to look for things that we can actually take the cube root of. Okay? In terms of exponents, it's going to be, we want exponents which are multiples of 3. So let's take out the largest multiple of 3 from here. So this we can rewrite as x to the 3rd power times x to the 2nd power. The largest multiple of 3 that's less than 7 is going to be y to the 6th power. So we rewrite this as y to the 6th power times y to the 1st power. And z to the 6th power is already a multiple of 3, so that's already fine. That's something we can evaluate the cube root for. The cube root essentially being raising it to the 1/3 power, right? So we essentially have to divide these powers by 3. That's how we're going to take the cube root of all of these. And now that 81, I'm going to split into a perfect cube, which is 27. So 27 is 3 cubed, right? It's 3 times 3 times 3. 9 times 3 is 27. Okay? So we're just going to take out one factor of 3 from here. And this now should all divide nicely. So I'm going to group the perfect cubes up front first. These are all the things that we'll be able to evaluate the cube root of. 27x cubed, y to the 6th power, and z to the 6th power. And the remaining terms we'll just keep under here. We can't do anything with them, so we'll just keep them nice and tidy, and this set of parentheses, we'll keep them under the radical. Everything else, we're going to evaluate the cube root of. Cube root of 27 is indeed 3. The cube root of x to the 3rd power, these are going to cancel each other out. We'll just be left with x. The cube root of y to the 6th, remember we're going to divide that exponent by this root power, which is going to give us y squared. Same thing with that z to the 6th. 6 divided by 3, that's going to give us z squared. Everything else stays under that radical. Okay. Next, let's talk about adding and subtracting with these radicals. Okay, so I've got example E here, the square root of 98 x cubed times y plus 3x times the square root of 32 times xy. Okay, so the same strategy we just used, we looked for, in the last example, we looked for perfect cubes first. Things that we could take out of this cube root. Let's try to do the same thing here, except with squares. So if there's nothing specified here, there's no numbers specified, this is understood to be sort of an invisible 2. This is a square root. Okay, so we want to look for perfect squares in our case. So we go ahead, we separate these things out. The biggest perfect square that we can take out of 98 is 49. 49 being 7 times 7, or 7 squared. Same deal. We want to look, what's the highest multiple of 2 that we can take out of x cubed? Well, x squared. We separate an x out, and then, well, with y, there's nothing to do. We just have to leave that as y. Here, 32, the biggest perfect square that goes into 32 is 16. So we break that apart into 16 and 2. And the x and y, well, there's nothing to do with those two. They're too low of powers. They're at the first power, so we can't do anything to simplify those. Same deal. Let's group these up front, the ones that are going out, and keep everything else that's staying inside within these parentheses. The square root of 49x squared is going to be 7x. The square root of 16 is just going to be 4. Now the nice part, the convenient part, is that, in fact, underneath these radicals, we have the same thing in both cases. We have the square root of 2xy. So you can sort of just treat this as a common term that we can factor out of everything. Another way you could think about this, we talked about substitution in the last video. If you wanted, you could think of the letter u as the square root of 2xy, and you could just think of this as 7xu plus 12xu, and then you could factor out a u from everything. It's the same idea. Okay? So that's exactly what we can do. We're going to factor out this square root of 2xy from everything. We'll have 7x and 12x left. You can combine those like terms, they're both x terms, and we'll get 19x times the square root of 2xy. Okay. Next example, now we're going to do a subtraction. We've got two cube roots here. Cube root of 64, m to the 4th, n to the 5th power, minus the cube root of negative 27 m to the 10th n to the 14th power. Now, when we see a negative underneath a radical, we should be some alarm bells should be going off, right? Because if we have a negative inside of a square root, that's going to cause a problem. We cannot take the negative, square root of a negative, right, number. But you can take the cube root of a negative number, because a negative number multiplied by itself 3 times will give you back a negative number. So that's fine. So whenever you have an odd power here, 3, 5, 7, 9, so on and so forth, you're allowed to have a negative underneath that radical. If you have even powers, 2, 4, 6, 8, so on and so forth, you cannot have a negative. Okay, that will be a problem. That's not something we can evaluate. It's not defined, at least not in the real number system. Okay, so let's go ahead and do our same procedure. Let's look for the perfect cubes that we can take out of here. Let's group them up front. So 64 is in fact a perfect cube. That's 4 times 4 times 4. This m to the 4th we can split into m to the 3rd and keep the other m inside this parentheses. N to the 5th, we'll take out n to the 3rd and we'll keep n squared inside the parentheses, right? So I'm taking out the biggest power, or multiple, I should say, of 3 from all of these terms. Same thing we're going to try to do here. What's the biggest multiple of 3 that we can take out of 10? That will be 9, m to the 9th power. Leave the other m in here. From 14, the biggest multiple of 3 we can take out of there is n to the 12th. Leave the n squared inside. Okay, and negative 27 is indeed, just like the example I just showed, a perfect cube, so we can evaluate that. Okay, so this comes out. Cube root of 64 is 4. Cube root of m cubed is m. Cube root of n cubed is just n by itself. Inside the cube root stays mn squared. Cube root of negative 27 is negative 3. I'm going to keep this in parentheses here for a second because we already had a negative out here to begin with, so we want to make sure we don't just lose track of these. Cube root of m to the 9th is m to the 3rd power. Cube root of n to the 12th is n to the 4th. Everything else stays inside. Okay. We go ahead and we make this into a positive. And conveniently, again, we see the same thing. We have the cube root of mn squared here, the cube root of mn squared here. And it's the same thing. We're going to be able to group these two terms together. In other words, you're sort of factoring this whole thing out. And you could write that up front if you like. You can write it back here. It's fine. It means the same thing. Okay? So as long as everything else is in the set of parentheses. So we've got the parentheses 4mn plus 3m cubed n to the 4th, all of it times the cube root of mn squared. Alright, so that's addition and subtraction with radicals. Let's think about multiplying. Okay, so example G. Now we've got 2 times the square root of 5 multiplied by, in parentheses, we've got the square root of 3 minus 3 times the square root of 6. So why don't we start off by distributing first? Okay, let's distribute and let's see what we can combine here. The good part is all of these radicals have the same power. So when two radicals that have the same power, they're 2 square roots or 2 cube roots or something like that, we can multiply, we can put together whatever's underneath this, as long as we just keep it under that radical. Okay? So that's exactly what we're going to do. So we've got 2 times the square root of 5 times the square root of 3, and over here we've got negative 6, right? 2 times negative 3, that's going to give us that negative 6, times this radical 5 times that radical 6. And now let's put both of these sort of under the same roof and multiply them. So square root of 5 times the square root of 3 is going to become the square root of 15. The square root of 5 times the square root of 6 is going to become the square root of 30. Okay, so this is now the most simplified form, and we're just going to leave it as this. 2 times the square root of 15 minus 6 times the square root of 30. Okay, and just be careful. You don't want to make the mistake of thinking that we could factor out. Right? I mean, we could do this. this is technically true, and then we could try to combine these two, but you'll have two radicals here, and that's just not, that's not simplified. So it's much better to just leave everything under one radical. And if they happen to be the same radical, then we can combine these coefficients. If not, we just leave it as that. We don't need to try to take out another radical to try to make this work. Okay. This would only be helpful if whatever we take out is a perfect square. Right? So if you had something like this, you could maybe take out square root of 4, right? And square root of 4 is a 2, so you could rewrite this as 2 times the square root of 15, which is what you have here. This is a case where it makes sense. This is not. Okay? All right, let's look at our next example. H, we've got, in parentheses, so the quantity square root of 7 minus the square root of 10 multiplied by the quantity square root of 7 plus the square root of 10. Now, you can go ahead and you can FOIL, or we can think about this recurrent pattern here that we keep seeing over and over again. We've got a minus b times a plus b in this case. So I wrote it in the other order, but you've got a minus b times a plus b. The same term is showing up here, and the same term is showing up here. And we've got a negative and a positive. And this is actually going to combine nicely. We can save ourselves a step by just jumping right to the a squared minus b squared. And this works out really nicely in this case because this square is going to cancel out with that square root. They're going to undo each other. Okay, so we're going to get the square root of 7 squared minus the square root of 10 squared. We'd go ahead and get rid of both of those. We're just going to have 7 minus 10, which comes out to negative 3. So this is going to work out really nicely. Okay. Now this is a case where we've got a plus and a minus, but unfortunately it's not adhering to the same a plus b, a minus b sort of thing, right? So we don't have the same terms involved here. So this one we're going to have to just FOIL out, and we're going to see what this comes out to. But the nice part is when we're multiplying two terms under square roots, or two constants, we can still find some sort of way to group them together. So we're going to have the square root of 2 times the square root of 8, negative 5 times the square root of 2, 3 times the square root of 8, and negative 15. Okay, so we go ahead, we put both of these into the same root. This becomes the square root of 16, which is a perfect square, so that's great. That works out nicely. Then here, just like we were saying before, we can take a perfect square out of this. So 8 is actually just 4 times 2. 4 is a perfect square. So this is, for this kind of thing, it's going to be really helpful to memorize your perfect squares. Okay. Just know a few of them. So 1, 4, 9, 16, 25, 36. I'd say up to 100. Just the first 10 of them would be really useful, because these are going to show up over and over again. It's going to be really nice to know when we can simplify these and not have to work with radicals anymore. Okay, so square root of 16 is 4. Negative 5 root 2 is going to stay exactly as it is. We're going to separate this square root of 4 times 2 as a square root of 4 times the square root of 2. Now let's see what happens. This is just going to become 2. 3 times 2 is going to become 6. Now, these two constants will combine nicely. 4 minus 15 will give us a negative 11. As far as these two go, well, they have the same radical, right? So this is no different than doing something like negative 5x plus 6x. We can put these together and just make this a 1x, right? That x in this case just being a square root of 2, right? So there's nothing to do with this, but we can, because they have the same radical, you can treat it the same way you would as a variable, right? Or you could imagine, like, you know, we could have factored out that root just like we did in the past, right? And then combine those negative 5 and that positive 6. And we'll get 1 in either case, so we'll get negative 11 plus the square root of 2, or 1 root 2, either one. Okay? Now, let's think about, for our last section, rationalizing denominators. Okay. So this is the idea of turning this denominator into a rational number, right, when it's not. So we don't like having square roots or cube roots or radicals of any kind in a denominator. That's not considered good form in math. Okay? And it makes it difficult to work with, right? If we want to go ahead and we want to do some operations, we want to find the least common denominator or something like that, these radicals are difficult to work with. So if we we prefer to put them in a more convenient form, something with a nice whole number or integer in the bottom. Okay? So the way this works, we're going to do the same process that we were doing last section, where we're multiplying by 1, but in a convenient format. So we can multiply the top and bottom by anything as long as it's the same thing, right? So in this case, if we multiply the top and bottom by the square root of 3, which really is just 1 in a different format, these square roots on the bottom will combine and become just a full 3, right? The square root of 3 times the square root of 3 is the square root of 3 squared. These are opposite operations, and you just get back 3, right? So this is going to become 4 radical 3 in the top divided by 3. This is considered now rationalized, and this is something that we can easily find a least common denominator with for other fractions or something like that. Okay? Let's look at a different example. So now we've got the cube root of 5 over x to the 6th minus the cube root of 4 over x to the 9th. All right. So let's see. So one nice thing is this looks like both of these powers are multiples of 3. So we might be able to just kind of go ahead and simplify, right? We can see what we can reduce these denominators down to first before having to do any complicated math, right? So let's go ahead and we can apply this cube root to the top and to the bottom of this fraction. The same thing here. We can apply the cube root to the top and the bottom. It means the same thing. Okay, so now we've got cube root of 5 over the cube root of x to the 6th minus the cube root of 4 over the cube root of x to the 9th. Now the cube root of 5 and cube root of 4, they're not going to reduce. Those aren't perfect cubes, so we're going to leave them as they are. But the cube root of x to the 6th, well, we can go ahead and we can divide 6 by 3. We're going to get x squared. No more radical. Same deal here. We're going to divide 9 by 3, and we'll have 3. No more radical. And now this is something that we can easily find a least common denominator for. So for this one, we can just multiply this by x over x. That'll give us x cubed in the denominator. We'll just have an x on the top. And now we can combine that with this fraction. Okay, so this is the value of rationalizing if we can. Okay, and that's going to give us x times the cube root of 5 minus the cube root of 4, all of it divided by x cubed. Now for our final example, let's consider something like this. We've got 1 over 1 minus the square root of 2. Now this becomes especially complicated because you've got a whole number here added or subtracted to a radical. So we can't just easily multiply or raise this to a power, right? There's not a whole lot we can do here to immediately get rid of this radical. But there is one strategy. And this strategy is called multiplying by the conjugate. So the conjugate is preserving both of these terms. So you're keeping the 1 as it is, you're keeping this radical 2 as it is, but you're changing that negative sign in the middle to a positive sign. And if you had started with a positive sign, its conjugate would have the negative sign. You would do the other one. Okay? And if we're going to multiply the bottom by it, then we have to multiply the top by it as well. Now, where does this come from? Why are we doing this? What we're doing is we're going back and we're forcing this again to this really important, really powerful property, the difference of squares. This is really powerful specifically for radicals because it's going to get rid of radicals by squaring everything. Okay? So this is a minus b that we have. What we're doing is we're really just multiplying by a plus b. And that's going to force the denominator to become squared. So it's going to become a squared minus b squared. And, well, the numerator is just going to go here, right? That's just going to stay as it is. But this is really nice. Well, now we've found a way to eliminate the radical from the denominator. So in the bottom, well, the square root of 2 squared is just going to be 2. 1 minus 2, we can combine those. We're just going to get negative 1. Okay? And, well, these are both divisible by negative 1. So we can even go one step further. We can just get rid of the fraction entirely. So 1 divided by negative 1 is negative 1. The square root of 2 divided by negative 1 is going to be negative square root of 2. Okay, so this is the process of rationalizing a denominator. In fact, we've eliminated the denominator entirely. We've got something that's a lot easier to work with. All right, that is a wrap on R8, which is the last section of our review chapter.